Okay, so let's continue where we ended last time. So last time we are in the proof, we are trying to prove the energy estimates for the null condition, and we have stated the proposition 7.6, and we have like written the e to the eighth power times p phi times phi t as a divergence, plus some remainders. So we also prove some estimates. That is, for example, we have proved that E0 is equivalent to 1/2 e to the eighth power times phi prime squared. So remember that equivalent means that you can control this E0 by a positive constant multiple of this right-hand side from above and also from below. Okay, we also proved that R1 is bounded by C0 epsilon x plus t to negative 1's power x minus x minus t to negative 1/2's power 3/2's power. Let me times t phi times phi prime. So remember that t phi is the tangential derivatives plus C0 epsilon x plus t negative 2's power x minus t negative 1/2's power times v prime square. Okay, so last time we have proved these two bounds. And to finish the proof of energy estimate, we also need to estimate this R2. So R2, we actually would prove that it has lower bounds. So unlike the previous two, unlike the R1, so R1 we estimate the upper bound for the absolute value of R1, but for R2 we actually just prove that it has a certain lower bound. So that would be enough for our proof. So let me just remind you that let me just write down the formula for the R2 here. If you want to know how we get this R2, why we have such an explicit formula, please refer to the lecture notes or our previous class. So we have this Q alpha, G alpha beta, V beta V t minus 1/2QT, G alpha beta, phi alpha, phi beta. So here, Q is actually equal to the radius of x minus t. So that is something we use to connect the estimates with our null condition. So because you know that qt squared equals q1 squared plus q2 squared plus q3 squared. So we can now use the condition of the null condition to get something is equal to 0. So that is the reason why we use this Q alpha. Also remember that we have a Taylor expansion for this G alpha beta. That is G alpha beta is equal to M alpha beta, which is the diagonal of -1, 1, 1. So it's a diagonal matrix, also something like the Minkowski matrix, plus a linear term G alpha beta lambda 0 partial lambda u plus some reminder, which is quadratic terms. So now we plug everything back, plug this formula, plug this Taylor expansion into the expression of R2. Then we would get R2 is equal to Q alpha M alpha beta phi beta phi t. So this part we just copy everything down using this Taylor expansion, and we did not do any actual computation. So this is the formula we get if we replace G alpha beta with ML alpha beta. And also we have Q alpha, G alpha beta lambda 0, phi beta phi t minus 1 over 2 QT, G alpha beta lambda 0, U lambda phi alpha phi beta. Okay, and also some remainders. So notice that the remainder is of size U prime square, Q alpha, the partial derivative of Q are all bounded. And also we have phi beta, phi t, or phi alpha, phi beta. So in conclusion, the remainders would be U prime square times phi prime square. So these remainders would be good enough. So we do not need to actually care about the structure of these things. So, but for the previous two rows, then we have to be more careful about the structure of the sum, because if you just use some preliminary estimates to estimate this, then you only get something like phi prime square times U prime, or even worse. So that is not enough in our proof. So we need to be more careful about the computations here. Okay, so if we take a closer look at the second row, then we can actually use null condition to control this directly. So, well, here is actually it is something you need to be a little careful about, because, well, okay, so let me just write down more details here. So remember that in the null condition I mentioned before, we have something like G0 alpha beta lambda U alpha V beta W lambda. This thing is controlled by TU times V prime plus W prime, sorry. So what I want to say here is that this would be just to estimate this would be a direct application of a certain estimate we have proved before, but it might not be of exactly the same form that you have seen before. So let me just explain this so that it will be more clear why we can use that directly. So the thing here is that you can just apply the lemma and get the estimate you like. You do not need to do any actual estimate. So probably in my lecture notes, I prove this again using null condition, but in reality, you don't need to do this. You can just apply a certain estimate before without like doing other things. So remember that we have this red estimates, this estimate here. That is something you can get if you apply the null condition. So you have three functions, three partial derivatives here. So using the null condition, you can write it as a tangential derivative multiplied by two usual derivatives. Tangential derivatives multiplied to usual derivatives. Tangential derivatives multiplied to usual derivatives. So the thing here is that in the first sum, in this term, you replace U with Q, V and W with phi in this estimate. Okay, if you do that, you will get the estimate for the first term directly. If you set U with U, replace U with U with phi, V and W with V with phi and W with U. So you can also use this estimate here directly to estimate this term. So you can just apply the lemmas there and get the bounds you like. So the second row here would be controlled by, let me erase this estimate and just write down the thing we have here. So the second row would be bounded by TQ times phi prime square plus phi prime T phi Q prime. Okay. And this is the first term. For the second term, you have tu times phi prime square plus t b times phi prime times u prime. Okay, also remember that q prime is actually bounded, so you don't have any q prime in the last estimate, so you can just erase this q prime. There's only one thing that you need to be careful about, that is this t phi, tq. Okay, so this term seems bad because it seems that you have two usual derivatives, but you don't have any tangential derivatives here. But the good news here is that tq is actually equal to 0, because q is tangential to the level set of q. Q is equal to r minus t. T is tangential to this light cone, so of course tq would be equal to 0. So this first term would actually also vanish. So we have, we can simply erase the first term. So the final estimate for the second row here would be, okay, I actually make a small mistake. I actually forgot one u prime here. So sorry about this. So we actually have this ut here. So that means we need to multiply everything by u prime, so that this is something we would get at last. So we have 3 cubic terms here. And in each of these cubic terms, we have at least one tangential derivatives. So that is nice. So this gives us the bounds for the second row in this expansion of R2. Okay, so finally, let's consider R1. The first row, that is the row with this M alpha beta, the Minkowski matrix. So we can do the computation directly. So you probably need to do some computation by yourself, but I can tell you that this is equal to phi t, phi r plus 1/2 phi prime square. Okay, so just do the computation like in the first row, in the first term, you take alpha equals beta equals 0, then you get negative qt phi t square. And when alpha equals beta equals some non-zero index, then you have qj, phi t, and that gives you a phi r. Okay, that is the first term. And then the second term is similar. So let me just skip all the computations here. So anyway, it might not still be not that clear what this term is, what this sum is, but let me also compute another thing, that is t. Sorry. So I actually claim that I can actually tell you that this underlined part, this underlined thing here, is actually equal to 1/2 times t phi square. Okay, so this might be a little strange, but let me do the computation here. So t phi square is equal to j equals 1 to 3 tj phi square equals j equals 1 to 3 bt bj plus omega j phi t square. So if you expand everything, you get bj square, take the sum, plus omega j square phi t square, also plus 2 phi j omega j phi t. So if you expand this square and take the sum, then this is, you get these three terms. The first two terms, if you take the sum, because omega j square, the sum is equal to 1. So the first row is equal to phi t square plus phi j square, take the sum. So the first row is equal to phi prime square. And the second row is equal to 2 times phi t times phi r. Because omega j phi j, take the sum, is equal to phi r. So in summary, t phi square is equal to 2 times phi t phi r plus phi prime square, which is equal to 2 times this underlying part here. Okay, so that is the computation So finally, we now have estimated all these three rows, and our conclusion is that R2 is equal to 1/2 T phi square. We can now replace it with this with a lower bound because we have R2 equals 1/2 times T phi square plus capital O something. So we can use this to estimate a certain lower bound for this term, for this R2. So it's equal to larger than equal to 1/2 T phi square minus a large constant times this two capital O here, that is U prime, phi prime, T phi minus CTU phi prime square minus C T phi T phi phi prime U prime. So that is absorbed by the term by these terms here. So I only have two terms if I consider this big O here. I also have one more term, that is C U prime square V prime square. Okay. So I have a lower bound here for this R2. And I also, so remember that my R1, I actually have this like X plus T and X minus T here. So I would like to do the same thing here. I can use the non-given bounds for U to replace this U prime, TU, and U prime square with the term we like with some bounds involving X and T. So this is something I need to prove here. So remember that, recall in our proposition, our assumption is that U prime less than or equal to 3, the L2 norm of this thing at each time is controlled by C0 epsilon. Okay, so this is our assumption in the proposition. By Clemens-Sobolev inequality, this is we get something like U prime less than or equal to 1 is controlled by C0 epsilon X plus T inverse X minus T negative 1/2 power. So this is what we get if we apply the Clemens-Sobolev inequality. So this also gave us the bounds for U prime. So the bounds for U prime is good. So we now have we have something like epsilon square, C square, C0 square, X plus T, -2, X minus T, -1 here. Sorry, this is the square. So this thing is for this bound. And here we just copy down the Clemens-Sobolev inequality to the right-hand side. So the first term is some good term because, the first term here is a good term because it's positive, because it's some norm of the T phi square. So you know that this is at least non-negative. The second term is good because we can control this using T phi prime and T phi times some given bounds depending on X and T. Last term is also good because you take the square of U prime, so which is also good. So the problem that you might need to be a little careful about is the second term, is the third term here. We have a bound for U prime, but we don't have a bound for TU. You can, of course, control this by U prime, but I mean, you can, of course, control this by U prime, but that bound is not good enough because here T is actually tangential derivative, but U prime is just some usual derivative. So you expect to lose something. So to estimate this, let's consider the following things. We will make use of this bounds for U prime less than or equal to 1. So using a certain estimate we have seen before in our previous class on the commuting vector fields, we can first replace these tangential derivatives with the commuting vector fields and get a good factor X plus T inverse. So we have this bound here. This bound is good because you have this actual factor X plus T inverse. And the question now is how we estimate the second thing, that is the commuting vector field applied to U. We now recall that we have this finite speed of propagation. Which is, I think, also a certain assumption in the. This is also the assumption in our proposition, that is, U satisfy the finite speed of propagation. So U is always 0 whenever x minus t is larger than or equal to a large constant, capital C. Okay. So because of this, we can apply the so-called what's the word? The fundamental theorem of calculus. We integrate the partial du from outside to inside, and because the solution vanished outside, we don't have any boundary terms from outside. So we get x. So tu is controlled by x plus t inverse integral x from x to t plus c, because x minus t larger than or equal to c. When this is true, then u equals 0. So we only need to integrate this from t plus c to inward u. So we have these things by applying the fundamental theorem of calculus. So of course, if the lower bound here, lower bound of this integral is larger than the upper bound here, then we actually just can, we already know that tu is equal to 0, so there's nothing to prove there. So here we can actually assume that this x is less than or equal to t plus c, so that we can actually get some non-zero bounds on the right-hand side. And now we apply the Klein-Sobolev inequality. We can now replace this bounds for partial du by the right-hand side of these things, because, well, that is the bound we get from the Klein-Sobolev inequality. And if we estimate this integral, then let me just write down the final answer. That is, you would get C0 epsilon x plus t negative 2 x minus t 1 over 2. Okay, so we get a bounds for tu. So if you compare this bound with the bound for u prime itself, then you see that you divide by x plus t, but you need to multiply this by x minus t. But x minus t is considered to be smaller than x plus t, so we can expect that the bounds for tu is actually better than the bound for u prime. So that gave us the bounds for tu. So we can now plug this tu bounds back to the bound for the estimate for R2. So our final conclusion is that R2 larger than or equal to 1 over 2 t phi square minus C0 epsilon x plus t negative 2 negative 1 x minus t negative 1 over 2 phi prime t phi minus C0 x plus t negative 2 x minus t negative 1 over 2 phi prime square, and finally negative c epsilon square x plus t negative 2 x minus t negative 1 phi prime square. So these three terms come from these three bounds. That is, this bound, this thing, the first term here correspond with the first row. The second thing here, the third thing here correspond to the second row and the third row. And also notice that the last row can be controlled by the second row, so we can actually just erase it and use the second term here to absorb that term. So this is the lower bound for R2. Okay, so now we have a bound for R1, R2, and now we can choose A here. So remember that in our previous proof, I say we take a weight e to the a's power, where a is a function of q, where q equals r minus t, and we assume that this is a C1 function on R. So at that time, I actually didn't tell you anything about what this A is, because we would actually not need these things in our previous proof. But here, I would say we need to choose this A so that e to the a's power, so here we was actually started consider how we choose A here. So let me do one more steps when I estimate this R1 and R2. So we would choose this A so that we can estimate the following thing. So remember that in our first step, we write some divergence plus some remainders. So divergence part is good. So we only need to consider divergence. So for divergence, previously we split them into R1, R2, but now to actually finish our proof, we need to combine them together. So it is important now to estimate the following thing, that is, R1 plus A prime times R2. So this, let me copy everything down here. That is, I get. Okay, so now let me copy everything down so that I don't need to like write down everything again. So again, I would like to estimate a lower bound for R1 and for this R1 plus A prime times R2. So this is for R1. So this, what I have just copied is for R1. So let me put it down here. Also, I would like to have something for R2. So not this one, this one. And remember that I need to multiply this by A prime. Oh, okay, so the first thing I need to mention here is that I would always assume that A prime is larger than or equal to 0, so I don't need to be worried about like changing the direction of the inequality when I multiply R2 by A prime. Okay, so we have this bounds here. Now let me tell you what this A is. This A should be. We choose A so that the limit of A at positive infinity is equal to 0, and A prime at each point is equal to 8 times Japanese bracket s to -1 minus eta's power. So here eta is a small parameter between 0 and 1. So this parameter also appears in the statement of this energy estimate. So this constant 8 is some large constant. Well, its value is actually not that important, I think, because probably you can choose some even larger number later, but the value is really not important. So let me just write down this 8 here without explaining it. But you'll see that we need to choose that 8 large enough so that we can get some positive thing at the end of the proof. Okay, if we choose our A in this way, then I can replace this A prime with 8q -1 minus eta. So probably it's a good idea to switch the order of these two parts. That is, I first choose my A, and then I do the computation. So Okay, so now let's expand the first product here. So we have 4 times 4 times q to -1 minus eta's power times t phi square minus c0 epsilon. So this 8 is absorbed by this cc epsilon. So let me just write it down without this 8. I have x plus t inverse x minus t -3/2's power minus eta. So -1 minus eta minus 1/2. And also remember that q is equal to r minus t. So we have a q here. The third term, c epsilon 0, x plus t -2's power q -1/2 minus eta's power b prime squared, because 1/2 -1 minus eta, so -1 minus eta p prime squared. The remaining term would be the same, but you notice that so now we notice that the remaining term, this term, is actually larger than this term, because same here, same factor, you have -3/2, but you have -3/2 minus eta here. So this term is smaller than this term. And similarly, this term is smaller than this term. So I can actually just erase this eta here and get this following bounds. Okay, so I now get a lower bound for R1 plus A prime times R2. It would still be better to do one more step. That is, okay, I can, let's consider the second terms here. Using the average inequality, something like A times B is less than or equal to A squared C inverse plus CB squared, where C is a large constant, for example, something like that. Using such an inequality, I can split the second term. I can write the second term as the following. That is, this red underlined part without this negative sign is controlled by so I expect that the first term is controlled by this term. So I can write something like q -1 minus eta t phi square. Sorry, this should be less than or equal to without any constant multiple, plus a large constant c times c0 epsilon square times x plus t -2 q eta minus 2 p prime square. So I need to like explain this in more details. So let me explain how we get these things. Okay, here's the thing. So we see that our goal is to put the upper bound on this underlined part. And I also hope that one of this, so I would like to write it as A times B, where both A and B are positive terms. So my goal here is that I would hope that A squared is controlled by this. So I would take A squared equals to q to -1 minus eta's power times t phi squared without this constant multiple of 4. So this is my a square. So how about my b? So we know that a square, b square, if we take the square part, if we take the square of this underlined part, I would get c square, c0 square, x plus t, -2, q, -3, v prime square times t v square. And now I divide this by q to -1 minus eta's power times t v square. So this gives us b square, which is the second half here. Okay, so I can now split my second term in this inequality, this underlined part, with a sum of two things. The first thing is controlled by the first term in this energy, in this estimate, and the second thing is something which would seem to be quite small. So if you prove this estimate, then just notice that the circle part is actually controlled by this circle part, because, well, you have -2's power, you have -1/2's power, you have eta -2, but eta is less than 1, so eta -2 is less than -1, so less than -1/2. So this tells us that this circle part would be controlled by the last term in the estimate above. So in summary, I have proved the following estimates. R1 plus A prime R2 is larger than or equal to 3 T phi square Q -1 minus eta minus C 0 epsilon X plus T -2 Q -1/2 phi prime square. Okay, because of what we have done before. So the second term can actually be, the second term here can actually be absorbed by the other two terms by using the average inequalities. So this gives us the bound we like. Okay, now let's end the final step of the proof. So let me also remind you that if you choose this A in this certain way, then another thing you know is that the absolute value is controlled by 1. So e to the 8th power is equivalent to 1. So I mentioned this last time, that is the weighted norm with this e to the 8th power is actually equivalent to the unweighted L2 norm. So that would be good enough. So we have proved, so let me just go back to this estimate here. So let's go back to this formula. If I integrate this with respect to x, at each fixed time, then the first thing, the time, we only have a time derivative because all the other things are divergence in the space, so you just get 0. So that is good. And also, my phi and my u are both compactly supported for each fixed time, so you don't have any boundary terms there. So we have integral partial t E0 dx. And also for these things, we have integral. So we have e to the 8th power, but e to the 8th power is equivalent to 1. So capital O No, let me keep this a to the power. E to the a's power times 3 t phi square. So let me replace this with larger than equal to so in reality, we only need this t to negative 2's power. So I don't need these bounds here. I can just relax it a little bit by setting x equals 0 here and setting q equals 0. That would make this factor a little larger. So p prime square dx. So I have such a bound. If I set capital ET equals E0 tx dx. So this is what I have seen, what I have done before. We have E prime t, the time derivative of E, is less than or equal to the integral e to the a's power p phi times phi prime plus this is a negative term. So sorry, I need to, yeah, so let me minus these terms. And finally, plus c0 epsilon t to negative 2's power phi prime squared dx. And now I apply Holder's inequality and to this term, and I recall that phi prime square, sorry, e to the a's power phi prime square is equivalent to E0. So finally, I know that so F is equal to P phi. So this is what we have if I apply the bound we have before. Okay, so now we can finish the proof. That is, you see that this circle part is exactly the same we have on the left-hand side of the energy we want to prove. And we also have the usual energy we had before. So one way to finish the proof is, again, we use the ground-Wilson inequality. So we now set a new function, ht equals et plus 0 to t r3 e to the a's power times 3 t phi square q -1 minus eta. All these things are taken time tau dx d tau. Then I have shown that h prime is less than or equal to c h1 over 2 f t L2 minus plus c0 epsilon t negative 2's power h. So the proof is now similar to the proof of the previous energy estimate. That is, we divide both sides by h1 over 2. So we get something like the time derivative for the square root of h is controlled by constant ft L2 plus cc0 epsilon t negative square root h. So now we use the trick we have seen in the proof of the previous energy estimate. So our final conclusion is that square root h is controlled by the square root h0 plus integral 0 to t square root the norm, L2 norm of f, and also multiplied by some integral 0 to t c epsilon. So something like this. So now you see that this gives us c0 epsilon. This is the end of the proof. So this is the end of the proof. So, okay, I have now just finished the proof of the energy estimate. So you can see that the proof of the energy estimate here is actually very similar to the energy estimate for the previous case, the general case, with that is you do not have null condition and you have a certain form of energy estimate. So using a null condition, we can actually get a good thing, that is we can get an actual positive term, which is this red underline here. So that would be a very important thing we need in our future proof for the global existence theory. Okay, so that is the end of this video, and in the next video I would explain the continuing argument of the proof for the global existence for the null condition.